Great day, great audience, and great presentation. So I would like to first thank the organizers of this event. So today I'm gonna talk about a hands-on inquiry into algorithmic bias in machine learning interpretability. So a little bit of about me. So I'm coming from a math, statistics, and economics background. So I have been a PhD candidate for a couple of years, and then I just decided to promote myself to PhD, which stands for PhD dropout, because that's just better, right? And I just didn't want to miss my last opportunity to drop out of an education institution to become a millionaire one day, right? I heard that's the key. So, so about this presentation, in this talk, I just try to be a little authentic. And basically present something that I myself couldn't find in the blog posts or videos or courses myself. So what I'm gonna do is basically I will present to you guys an image classification model that separates dogs from wolves, which is a pretty standard application, right, using Keras. And we'll basically use our own image data instead of getting that prepackaged, nice, standardized, cleaned up from a Python or R library. And we will build an awesome model which is going to fail miserably. So you may be wondering how that is possible, but you'll see. And we will come back and explain why the model was looking so great and then why it failed so badly using Lime, right? We'll interpret our machine learning model. And we'll basically discuss the pragmatic and ethical aspects of the issue. But I think what really makes my presentation unique is we'll deal with puppies. And you know, puppies are always great. So yeah, there you go. The data set consists of 45 dog images and 45 wolf images. So I think I would just like to pause here and just enjoy the beauty of these pictures. Just cuteness, right? So in total, we have 90 data points. I mean, 90, which we are going to split into train and validation sets, not test set necessarily. I know that's this more standard way, right? Train, validation, test, but I'll just do train and validate. And I will use 66 or 67% of this data in training and the remaining 33 in testing or validating the model. So basically we'll train an image classification model on just 60 images, 30 dogs and 30 wolves, right? I mean, we can't really expect it to really perform well, right? I mean, if it did, it would for sure fail on the 33 holdout validation set. So let's see how we do. The model, of course, I have some, a lot of data preparation effort before this, and this talk is more on the why and what side of things more than how. So this is just a tiny snippet of only the modeling training piece of the full workflow, which is, as I believe anyone in this room can tell, extremely standard, extremely simple. We just validate, do the train test split from the scikit-learn, and our test size is 33%, as I mentioned. And after I do that, I just initialize my Keras model. And as you see, it's not deep or anything at all. It's a pretty easy, I think the easiest feed-forward network, right? And then we'll just have 5 epochs to train this. And just look at the accuracies of each epoch, right? The last one, it comes close to 85 and 86%. So this is a little surprising, right? Just on 60 data points, I mean, how can you reach this? So maybe we just overfit the model, right, to the training data. So let's just validate this on the held out set, which is 33%. So you can look at the little code snippet here. I basically, this is the actually right way of evaluating a keras model's performance, just by calling the built-in model.evaluate function inside the keras library. And it shows me that training accuracy is 85%, which we basically just saw, and validation accuracy is 83%. So, which means I can build an image classification model on 60 images, and it will perform fantastically on the held out data set as well, that it didn't touch, right? There's no cross-validation here, there's no optimization, no model selection, it's just one run over the data, get the model, see how it performs, and we're done, right? So, okay, let me check. We said cross-validation, we said hyperparameter tuning, we said all these techie words. So, a Dilbert break, right? So Dilbert's boss goes, I need to know why moving our app to the cloud didn't solve all of our problems. He goes, you wouldn't let me re-architect the thing, right? And the boss goes, just put it in containers, right? Dilbert goes, you can't solve a problem just by saying techie things. And the boss goes, Kubernetes. So I'll just assume that we already said Kubernetes. So, and let's just deploy this. All right, ready? Kubernetes. There you go. It's deployed, right? Just saw the light of the day. And we now are accepting new data coming into our servers. Whatever this application is, this is just a simple exercise, right? It may be a healthcare model, it may be a financial model, it may be a admission type of model or recruitment, HR type of model. But based on the data that we had in hand, just 90 records, we built it. We have incredible confidence in this model. Now we just deployed it, and we're accepting, opening the gates and welcoming new cases to evaluate, right? So, I basically have just 6 images here, 3 puppies and 3 not cubs, just wolves, pretty vicious-looking wolves, I'd say. Let's actually see, let's test the model, right? This is the true test, right? So let's see. It's very simple. So just wanted to include this little snippet here just to basically describe that I'm just processing and standardizing the data just as I did in the training phase, and just simple resizing to 100 pixels, 100 by 100, and putting that in a loop so that this code is just going to show us in a minute each image and the classification, right? That's the last line. The print line is going to tell us how it classifies things. All right, so let's see. Let's go one by one, all right? And we'll go yay or nay, when, depending on if it's successful or if it fails. So the first case, already failed, right? This is a nay. But I think it may still be the case, right? This is a husky puppy. They look like wolves. So this may be the case. I mean, still, I think we haven't lost our faith in the model. So let's go to the next case. This fluffy little creature, it is classified correctly. So awesome, we're on track. So the next one, which was the flying cuteness, or whatever you want to call it, the flying little puppy of ours, which is just classified as wolf. I mean, come on. This is just unacceptable, right? How can this be the case. And I'll actually share the full code of, as an IPython notebook so that you can see that I'm not just copying, pasting, whatever I just wanted to form the story as. And this is really the performance or the predictions of the model. So this broke our hearts, I know. So let's just go to the 3 new WOF images and see how they're classified. I'll just present all 3 at once so that to make this as least painful as possible. So, all right, there you go. All 3 are classified as dogs. Now, I will show you the real pain, which is this picture. So you have a problem when your model confuses little puppy with a vicious wolf, right? Mislabels these 2. I mean, this is unacceptable, and I think at least the teenagers on social media would kill us for this, right? They wouldn't tolerate that. So we may be wondering, how come it was that successful in the training, validation, but in the true test, it failed so badly, right? I think it classified only one case, one sample correctly, which was the yellowish-looking fluffy one. Let's just we have a problem to explain here, right? Why did this happen? So basically, we'll just go back to this picture. We'll try to understand why it classified the little flying cuteness as a wolf and the vicious-looking wolf as a dog. So, all right. So this is just a very high-level summary of variable importance, right? So when we talk about variable importance or feature importance or attribute relevance, whatever, I think many terms to denote that, right? So you basically talk about 2 things, two phases of that question. So the first phase is which features are the most important to the model overall, right? So this is basically, this tells us a story about the training phase, which attributes were the most useful. This is basically the feature importance or attribute relevance analysis or whatever you want to call it, right? This is not what we're interested in. We don't really care about this. We care about the importance of attributes that caused this failure over here. So after deployment, how do we get the contributions of each attribute to the final decision of a machine learning model? So we have, in general, 2 approaches to this. One, we either open the mathematical algorithm, right? If it's simple enough. If you can do it, right? This may be preferable. Just 2 examples, pretty standard examples, is if we have logistic regression, we know that it's just one equation, right? Just one linear equation. So basically, we answer the question, how far am I from the average guy? And then we already have the coefficients. We can just multiply things and then sort. Then the top variables are your most influential variables that led to the model's decision in a particular sample, right? Or in a random forest, we know that random forest is basically a bunch of trees that basically traverse or branch out that start from the node that's called, maybe it's usually called bias, and then it traverses, and we have certain statistical parameters that we monitor, and then we finally come to the leaf, which is basically the classification. So we look at that in a random forest. So we can basically express this relationship as just a mathematical one-liner, and they're already pre-built, pre-packaged solutions that does this for you for random forest, right? Or you can just say, I don't really care about the mathematical details of things. I'll just go model agnostic. So the 2 main approaches to model agnostic explanations which actually people mean when they talk about interpretability is lime, right, and SHAP. So these are slightly different than each other, but I think as a summary, lime is just a subset of SHAP. SHAP is like more, it just encompasses a little more strengths or attributes than lime does, but we'll just use lime in this example. So how lime works is it basically takes the sample that you want to explain, right? So you're basically asking the question, hey, you just told me that this image is wolf. How did you come to that conclusion? And lime says, okay, give me that sample, perturb it, right? And give me basically as much variation of that image as possible so that I can score each and every of them and I can fit a linear model to closer to the decision boundary. Even though the decision boundary can be highly complex and non-linear, lime explains things locally, right, around, in the vicinity of the sample that we give to it. So for that reason, and again, the code behind this, I will, please stay tuned on maybe my GitHub page or maybe another presentation. So we've perturbed the dog image as follows, right? So these are just sample random 3 perturbations of the dog image. And I believe I have 100 of these. So when it comes to the wolf image, these are just sample 3 perturbations. So basically we'll run this through an algorithm that's going to include some weighted linear models, and basically that's where the magic happens. And then we are presented the following picture by the lime algorithm, which is, lime says the first image is a wolf because of this attributes, because of these attributes, and the second image was a dog because of these attributes of the image. Now, this is pretty striking, right? It is basically classifying dogs versus wolves based on attributes or features that have nothing to do with being a wolf or a dog. So, this basically is a demonstration of how bias in training data is only going to get reflected in the results, how prejudices, how our own perceptions, how our past mistakes in labeling that data is only going to be reflected in our in the results of the model, regardless of how complicated that model is. So actually, we can come back to the training sample, and we can see, just take another look at. So there you go. This is the reason. All dogs had a green background. They were all in a backyard or a playground or a nice forest and whatnot, right? And all the wolves were in mostly white backgrounds, which is snowy, more harsh, and there is no basically sign of life here, so that's the type of background. People use the word concomitant, right, that came with these images. Now, you may be asking, who cares, right? It's just a classifier between 2 images. But now, I think the main question, the main ethical or philosophical question is, in this example, I intentionally chose these images this way, right? Just to show you guys how the bias is going to only get reflected in the results. So the question is, what happens to the cases in our daily lives that we are basically subject to 2 groups, right? Different groups that are basically in the past subject to a nice background versus harsh background, right? Green background versus white, snowy, cold backgrounds. So what happens if we try to build solutions, machine learning solutions, which is, I mean, use all the buzzwords, right? Say Kubernetes 1,000 times on that data and still get the saddening result, right? So let's just look at some everyday examples of bias in AI. So there you go. So the first example is the recruiting tool, the HR AI system that Amazon used, and basically they discovered that this is just biased against women. So why? Because women always had the snowy background, right? They didn't really exist in that data set. So their data set did not really have an opportunity to, their model did not have an opportunity to really learn from those individuals, right? I mean, they didn't have an attribute of this is a female versus this is a male, right? But still, there are certain characteristics that the algorithms may be complex enough, more than we think they are, right? And then learn basically female names, female hobbies, or female, whatever you can think of in a resume, right? And at the end, it is just going to continue to recommend hiring more male technical experts, right? And the second one is AI is sending people to jail and getting it wrong. Basically, in our courthouses today, judges are using AI models recommendations in their bail decisions, or in their decisions that have the potential of impacting people's lives altogether. I mean, just introduce one dummy variable to your data set, to your right file, credit file or legal file, whatever, right? It's just going to permanently change your trajectory of your life. And they're using this. And it is shown by multiple experts or multiple referees, I would say scientific referees, that all it's doing is just replicating the past mislabelings or past frequencies, right? Which is one ethnic group may be more associated with crime. And now what does the AI do in that case? Again, does the same thing what the Amazon's hiring algorithm did. Basically just continue to recommend what was happening in the past. Continue labeling the groups that had a snowy, harsh, cold background as wolves, as vicious creatures. And the ones who are coming from green backgrounds, nice, spring weather and nice temperature, would basically be labeled as, okay, I am going to approve your bail application, right, to a criminal, potential criminal. So the third example is, this is pretty striking. I think there's a documentary about this. I couldn't really find that documentary. I think it's not commercialized yet. I think it was presented at a cinema or movie festival or something. That this lady from MIT realized that facial recognition applications did not detect her face. She's an African-American lady. Her color was totally invisible to the algorithm. And how she saw that is, she said, okay, let me just put a white mask, right? As you can see in the picture in the background, the tool says, okay, there's a human here, right? So again, bias in the data, the reason is, right, the algorithm probably didn't see enough African-American data points to train on. And basically that was the result. So, and probably the last, this could be the funniest. So Microsoft launched a chatbot, right, a couple of years ago, 2 years ago probably. And it got deployed, and it was a reinforcement learning. Basically, you would learn from from young people aged 15 to 24, or maybe 18 to 24. And eventually, all it learned was cursing, doing, discriminatory comments and racist comments. And they just had to rush to kill this, right, to take it down. So you can just go ahead and read details on just 4 examples that I'm presenting here. So this basically lets us face our prejudices. So we are fueling the model with our own prejudices and past mistakes, maybe, or maybe past associations, right? It may be statistically, solely statistically and mechanically true that when you just look at a given data set, right, certain ethnic groups, certain minorities may be more associated with crime. That may be statistically true, right? Or women, you just take random, just go out on the street, take random 100 guys and 100 women, you may come to a conclusion that, men usually are better at math, stats, quant type of fields, and ladies are more they're just better in more artsy things, more verbal things. But again, this may be statistically true, right? But the next lady that's gonna step into our machine learning model, which we deployed after training on that imbalanced or unfair data set, is going to label the next lady as less capable of being good at a technical job than a random male, right? So there's a very thin line here between what is statistically and mechanically true and what is actually true or philosophically true or ethically true, right? So all our prejudices should be, we have to be aware of what we are pouring, what we are fueling our models with, regardless of how that model, how complicated that model is. So I think this can just be the line of the day. In the presence of confounding factors, right, correlations appear as causations. Just take a sample. If you see one minority is more associated with crime, you may think, okay, there's something inherent here in that group that if I'm a judge, I wouldn't really be wrong in labeling the next member of that group as a criminal. I would be less wrong. Statistically, that is true. But is it ethically true? All we're doing is reinforcing our own past mistakes that existed in the training data and got reflected in the result, right? So whatever happened in between is just techie talk, right? It's just Kubernetes. Nothing is wrong with Kubernetes, right? But it's just techie talk. So, in conclusion, if you, as Dilbert, if you collect optimistic data, put it in the context of bad analogies, season it with salience bias, add herd instinct, pitch of confirmation bias, and present that to your leader as a strategy, right? You really have to have a leader like his pointy-haired boss to say, okay, why do I always get the hard part of adding my leadership on top of that, right? You can't get away with that. So, I really like the second one. What do you get when you combine cognitive bias with inaccurate information? So the truth is, the business strategy. If the business strategy is, business strategy, criminal law strategy, or hiring strategy, or education admittance strategy is based on or biased by bad data and bad basically approach, no matter what you do, all you get is just a business strategy that looks like this, right? So, all right, so please stay tuned, and maybe we'll meet at another conference. Thank you.
Let's see. We have a couple of questions for you today.
Of course.
Okay. All right. Did you enjoy that? Yeah? Okay. How could Lime be implemented and interpreted using tabular data?
I think it's, so I benefited a lot from certain tutorials on the web, but the main difficulty that the challenge that I had was modifying my data enough so that it would be suitable for the Lime algorithm. So there, in a tabular data, in a image data, voice data, and whatnot, I think the main challenge is really processing the data to make it suitable for the algorithm to digest. I think that's the main problem. And I think image and voice, or or video, these are really the complicated ones. If you're dealing with just a tabular data set, things should be more straightforward. I haven't really built anything like that, but it should be easier. That's what I would say.
Amazing.
Anything else?
Oh, yeah.
All right, yeah, go ahead, please.
You think you're off the hook now?
Oh my goodness.
What do you consider to be female hobbies?
Oops, that's, I didn't, my goal was not to label any hobby as female hobby, but I think my point is there may be certain things that a model may learn to classify against, right? It may say, if I see things like maybe football or boxing or like more kind of harsh sports in nature, which statistically and mechanically is more associated with men, these resumes are more associated with successful software engineers, right? I have more of these people, of resumes of this type, than the resumes that contain softer hobbies, that I cannot think of. And I think I'm just so afraid of making a political mistake here.
Okay. What approaches do you recommend for correcting an unconscious biases in models and data inputs?
That's a great question. I actually wanted to specifically mention that in this talk, I just intentionally didn't go to that space because that's a huge independent area or facet of things that should be investigated. But there are a lot of attempts, and I have to say these are very recent, right? It's a shame that we're building awareness about these ethical issues just now. Like all these news, all the realizations that I presented are from just a couple of years ago, or maybe a couple of months ago, right? And there's a recent effort to correct these issues that are in the heart of our society today, which are determining our courses of lives. So the simplest one would be, of course, just look at the sample sizes. If you have more good people, you're building a classification model, right? More ones than zeros, then your model is just going to learn to label next person as a one, because it's just going to perform better if it stayed on the side of the favorable group. So I think I am planning another presentation on that aspect. So maybe we'll touch base again. All right. Well, thank you.
Have a great
Appreciate
time.
it. Thank you. Thank you.